Bismillahirrahmanirrahim. My name is Malak Bal. I am from BS Chemistry Department, and the topic of my practical is determine concentration of KMnO4 solution using spectroscopy. Introduction. A spectrophotometer is an instrument that measures the amount of photons, the intensity of light absorbed after it passes through sample solution. With a spectrophotometer, the amount of a known chemical substance concentration can also be determined by measuring the intensity of light detected. Depending on the range of wavelength of light source, it can be classified into two different types: UV visible spectrophotometer and IR spectrophotometer. UV visible spectrophotometer uses light over the ultraviolet range 185 to 400 nanometer and visible range 400 to 700 of electromagnetic radiation spectrum. IR spectrophotometer uses light over the infrared range 700 to 15,000 nanometer of electromagnetic radiation spectrum. In visible spectrophotometry, the absorptions are the transmission of a certain substance can be determined by the observed color. For instance, a solution sample that absorbs light over all visible ranges. Light transmits none of visible wavelengths appears black in theory. On the other hand, if all visible wavelengths are transmitted, light absorbs nothing, the solution sample appears white. If a solution sample absorbs red light, it appears green because green is the complementary color of red. Visible spectrophotometers use a prism to narrow down a certain range of wavelength to filter out other wavelengths so that the particular beam of light is passed through a solution sample. Beer-Lambert law. Beer-Lambert law, also known as Beer's law, states that there is a linear relationship between the absorbance and the concentration of a sample. For this reason, Beer's law can only be applied when there is a linear relationship. Beer's law can be written as A is equal to epsilon naught into LC. A is the measure of absorbance. Epsilon is the molar extinction coefficient or molar absorptivity, and L is the path length. C is the concentration. The molar extinction coefficient is given as a constant and it varies for each molecule. Absorbance does not carry any units since epsilon and path lengths are known. We can calculate the concentration C of the sample. Apparatus. Test tubes, test tube holder, measuring cylinder, pipette, Erlenmeyer flask, spectrophotometer. Chemicals required: KMnO4, water. Procedure: preparation of 100 ml of a stock standard solution of 0.001 KMnO4, accurately weigh 186 milligrams solid KMnO4, transfer quantitatively to a 100 volumetric flask and fill to the mark with water. This is the stock solution. Prepare a 6 standards in 100 ml volumetric flask with concentrations of 0.0004 molar, solution 1, 0.0002 molar, solution 2, 0.001 molar, solution 3, and 0.0005 molar, solution 4 by diluting the stock solution prepared in step 1 and the system as serial dilution. Rinse one of the cuvettes with distilled water and fill it with water. Put the cuvette in the sample compartment. This is the reference solution. Set the wavelengths to 400 nanometer. Then set the absorbance to 0. Rinse the second cuvette once with distilled water and once with standard solution number 1. Then fill it with standard solution number 1, 0.001 molar KMnO4. Put the cell in the cell compartment. Measure the absorbance at 410. Repeat this procedure, steps 3 and 4 above, for the two cuvettes at wavelengths 420, 430, 440, 450 to 600 nanometer. First setting A is equal to 0 for the cuvette with water, then measuring A for the cuvette with 0.001 KMnO4, recording the absorbance at each wavelength, recording data table. Prepare a graph of absorbance versus wavelength and determine lambda max. Set the wavelengths at 550 nanometer lambda max. Place the cuvette with distilled water in the cell compartment and again set the absorbance is to 0. Measure and record the absorbance of each of the 6 standard solution. Starting with the most dilute standard. After each measurement, rinse the cuvette with the next standard, not with distilled water. Draw a plot having x-axis as concentration and y-axis as absorbance at lambda max 550 nanometer. Use base law to calculate epsilon for KMnO4, giving the cell width to be 1 centimeter. Observations and calculations. This is the absorption spectrum of KMnO4. At 410 wavelength, absorbance is 0.056. At 420 wavelength, the absorbance is 0.033. And at 550 wavelengths, the absorbance is 2.019 and so on. This is the absorption spectrum of KMnO4 between absorbance and wavelength. And the highest point shows the value of lambda max, and the value of lambda max is 550 nanometer. Absorbance of solutions are different concentrations. At lambda max equal to 550 nanometer, at 2.5 into 10 power minus 5 concentrations, absorbance is 0.033, and at 0.00005 concentration, the absorbance is 0.186 and so on. This is the graph between absorbance and concentration. This graph shows that greater the concentration, greater will be the absorbance. Result. The result of the experiment shows greater the concentration, greater will be the absorbance. The value of absorbance increases as we increase the concentration of KMnO4 at lambda max, that is equal to 550 nanometer. Result of the experiment verifies Beer-Lambert law. Discussion. On the graph, trend line does not pass through exactly zero. This is as expected. It may be due to the statistics of the data point, which are not exactly on the straight line due to the random errors in the concentration or the absorbance reading, or the fact that there is a remaining solution absorbance relative to the blank for the standards. Finally, trend line slope is the molar extinction coefficient. The equation y is equal to 0.1609x minus 0.1293 for this application should be read as A is equal to epsilon dot C plus constant with the constant equal to intercept. That's all from my side.